All right, why don't we get started? So it's a pleasure to have Rachel Osten here today to talk to us about STROBE-X and stellar activity. Rachel is one of the world's leading experts on stellar activity at every wavelength that exists. So whenever you're ready, take it away, Rachel.
Okay, sure. Thanks very much for the invitation, Tom. I put these slides together. Unfortunately, I was kind of running short on time and worrying about having an unprepared talk. And then I just started assembling slides from other talks that I've given. And I realized I probably have more than we'll fill this time. But I thought it would be useful for you all just to give you a sense of the kind of broad outlines of what is interesting and important and motivating in the science area. Some specific science questions that I personally am interested in that have relevance to STROBE-X, and then at the very end, talk a little bit about how STROBE-X could contribute to this science area. So let me see if I can get going. So I'll start by talking about the Astro 2020 science themes. Like I said, I'll touch on some outstanding questions on stellar flaring events, and then come back to the specific topic of this proposed mission. So Worlds and Suns in Context was one of 3 science areas called out for special emphasis in the coming decade by the U.S. National Academy's Decadal Survey in Astronomy and Astrophysics. You can see the little graphic off to the right, just pointing out the interdependence of advancing our knowledge of stellar astrophysics and our knowledge of exoplanetary astrophysics. Those two are intimately entwined from formation through evolutionary, all evolutionary phases. And one of the particular emphases of the decadal was setting up a suite of facilities and telescopes that can probe the identifying habitable Earth-like worlds and understanding that in its entirety and in its complexity. And their recommendations for this particular science theme span the electromagnetic spectrum from X-rays, infrared, optical, UV, radio, millimeter. And so that's what the icons at the bottom of that screen are. Of relevance for this particular area is something that has a topic that has grown in interest in the last 20 years, and that is illustrated by this plot on the left, where I just show ADS search results for refereed papers that have both exoplanet and space weather in their title. And you can see it goes from, one or a few to now more than 150 or more than 100 papers being published each year on this topic. So this illustrates the kind of both the up and coming nature of this. It's very interdisciplinary, requires knowledge of not just exoplanets and not just stars, but our sun, our own planets in our own solar system, and how those all interact. Astrobiology is another component to this. So just illustrating the interest and the motivation in the last couple of years for this area. From the X-ray perspective, when we think about impact on stars, we need to recognize that the amount of a star's high energy radiation changes during its lifetime. For stars in the cool half of the HR diagram, this is it's a function of age, but it's also a function of the star's rotation history. The graph that you're seeing here on the left is a simulation for a solar-like star, where there's some assumptions built into the very early stages and the very late stages of evolution. But the path that particular star takes in terms of how much ionizing radiation its corona is releasing varies dramatically depending on what the rotation history of the star is. So you can see that for the fast rotator, slow rotator, and then green is sort of in between. That is important because the amount of the high energy radiation that the star is releasing, as you can see on the plot on the right, influences it influences any atmosphere or any planet that's nearby. And this is just a quantification of that mass loss rate, the hydrogen loss rate, as a function of the X-ray ultraviolet XUV flux. And those factors will ultimately are important in determining whether the star will irradiate away all the planet's atmosphere. This is from the same paper that I showed you plots from yesterday. The previous slide. So the simulation is for an Earth mass planet around a solar-like star with these different rotation history profiles. And each of these contours gives a snapshot of slow rotator or fast rotator at 100 million years or 1 billion years. And you can see the axes are planet mass versus the atmospheric mass, initial atmospheric mass for the exoplanet atmosphere. And depending on where the particular cases are and the particular rotation profile and age, you either are in a safe zone where the entire atmosphere is kept, or you're in a danger zone where, you know, most of that atmosphere would have been lost. Okay. So our expectations are that basically all stars on the cool half of the main sequence exhibit magnetic activity to some degree, but some are more equal than others. And there's this sort of what I like to call the usual suspects of the most active stars. Just keeping in mind, these are normal stars. So I showed you before that the rotation of the star was important. M dwarfs that have very deep convection zones drive frequent and extreme magnetic activity. Young stars, because they're young and they're rotating rapidly, exhibit very enhanced levels of magnetic reconnection related activity. And stars that are orbitally bound to each other, they're tidally locked, enforce fast rotation. And that's the scenario that's shown on the right hand side, where you have tidally interacting close binaries. Mass transfer is not taking place, or it's very minor, but because the two stars are close enough to gravitationally interact, the stars spin much faster because of that coupling between the spin and the orbit. And so they kind of act like very young stars, and they drive extreme magnetic activity. So flare, so I mentioned high energy radiation, just, you know, as a sort of general property of the star and how it's changing over evolutionary times. Flares can happen on they do happen on much shorter timescales. And they have an impact per event that's been studied in astrobiology, several astrobiological papers. They also have a cumulative impact. And the point I want to make here is that this depends a lot on the assumptions that you make about how you're treating these events. We have a wealth of information about the sun and its flares, its coronal mass ejections, its energetic particles. Based on what we know about other stars, we think that the same physics is at play, and I'll get into that in a little bit. But there are a number of assumptions that have to be made when you're going from a stellar observation, which tends to be fairly sparse, and the kinds of scalings that you assume are going to happen so that you can do calculations like this one from Segura, which is a few years old now. There's a more recent paper by Tilley in 2017. Essentially, you take your planet and you make some assumption about what its atmosphere looks like, and then you have your stellar flare, stellar eruptive event go off, and you have to make some assumption about how the radiation and the particles and the accelerated particles relate to each other. What this paper found, and other papers since have confirmed, is that if you're only talking about the radiation, right, so we've got high energy radiation along with UV, optical, radio, that in and of itself has a fairly minor impact on the instantaneous any changes in the atmosphere of the planet. However, once you start adding in particles, things get very problematic. Okay, and that's what's shown on the right, that basically over a time scale of several months, the fractional change in the ozone column depth of this putative Earth-like planet around an M dwarf goes away and takes several decades to regenerate. But that is assuming a very specific set of scaling. And we're at the point now where we can start to investigate those scaling relations and their validity in other stellar events. Okay. Here is my standard movie about just what we think these flare events look like. It starts with magnetic reconnection, which you're seeing here as these magnetic fields are moving closer to each other. That liberates energy that then goes into plasma heating, particle acceleration, shocks, and mass motions. So our understanding of stellar flares is that they involve all layers of the stellar atmosphere. As I mentioned, there's a bunch of different physical processes. And based on the observations that we have to date, we see that there's a good correspondence to 0th order, maybe even 1st order, between what we see on the sun and what we see on other stars. So there's an important kind of distinction to make, that when stellar astronomers talk about these kinds of events, we're usually observing just the radiation, the electromagnetic radiation from these events, because they're, light years away from us. Solar physicists recognize that there's the solar flares, which I'm showing you in this movie. This is a coronal radiation, and you can see the really amazing twisting and reconfiguring of magnetic fields, the brightening of the plasma that's happening as this plasma is being heated. Those are often accompanied by coronal mass ejections. This is for the same event as what I showed you previously. The size of the solar disk is that white circle that's being occulted. And you can see that there's a very large scale event of material that's being blown out of the away from the surface of the sun and into the heliosphere. So it has very large scale impacts. There is a recognition that those two components are accompanied by these energetic particles. Now, this movie is from a different event as from the first two things that I showed you, but that fuzz is the impact of MEV particles hitting the detector of I think it's the SOHO spacecraft. So we see evidence both in space and on the ground for energetic particles that have energies that stretch up to giga electron volts being accelerated during these solar flare events. So in recognition of things like habitability and space weather, which we're familiar with from our Earth perspective, the geo-effective part of these eruptive events is not the flare, and that sort of corroborates what I pointed out earlier from the astrobiology papers. It's actually the CME and the energetic particles, and their effect depends on where the Earth is in its orbit and where the event originates on the sun's surface. So it indicates a level of complexity beyond, do these things happen, but where did it happen? Where was the planet? Was it magnetically connected to that region on the surface of the star? So one question that's come up in the last decade or so, well, it's been a topic for discussion long before that, but observations with the Kepler Space Telescope have revealed evidence for very energetic flares on apparently single solar-like stars that have slow rotation periods that are similar to what we see on the sun at its current age. The top plot in the middle just shows an example of that. So you can see the star spot modulation, and then the very impulsive increase in the intensity as a function of time. That's a white light flare. When you look at the aggregate statistics from these on slowly rotating G-type stars, you can see flare energies that extend up to 10 to the 36 ergs, which is about 4 orders of magnitude larger than the biggest flare that we've seen on the sun in historical records. So there is a natural question that comes up about, you know, if other solar-like stars can make these super flares, what's the likelihood that the sun could do this? The plot that I'm showing on the right is just that was a model, just kind of a toy model looking at the relationship between a star spot size and the amount of energy that could be released in a flare. And for some of these super flare events, you need fairly large sunspots. All right, so that could be a whole talk in and of itself. So I'm not gonna go down that route. I want to talk about one particular area that has been enabled by the SWIFT satellite, which I think is relevant for STROBE-X, and that is a unique opportunity to observe some of the largest stellar flares. So this was fairly unanticipated, I would say, but in hindsight, it is a natural expectation of SWIFT's capabilities. And so by extension, you think about what STROBE-X would be able to do. SWIFT was meant to detect and follow up gamma ray bursts. Gamma ray bursts have an impulsive hard X-ray emission followed by an afterglow at soft X-ray and ultraviolet optical wavelengths. The intensities are very large, but the capabilities that SWIFT has to be able to be sensitive to transient hard X-ray emission and then swiftly reorient the entire spacecraft to get those narrow field instruments observing, that ends up being ideal for studying some of the very bright and very rare events that are happening on the surfaces of nearby stars. And it has happened about a dozen times over SWIFT's lifespan. So this is by no means crowding out any of the other fantastic science that SWIFT does, but it's a region of parameter space that we would not have any insight into if were it not for SWIFT. There have been pointed observations, lots of pointed observations of active stars, but the event rates are large enough that we just would not, you know, we've seen things similar in nature, but SWIFT offers us an unbiased way to probe these events. What we're seeing are very energetic, as I mentioned, up to 10 to the 36 ergs for M Dwarf stars, even higher for active binaries, peak flare luminosities in the X-ray that exceed the bolometric luminosity. That's something that you normally think of as changing on evolutionary timescales, and here it's changing on timescales of minutes. Peak temperatures in the 100 million degrees. These originate from those usual suspects that I mentioned before, active binaries, M dwarfs, young stars. So let me just go through a handful of the papers that have been published recently, or on this topic. The first of these events was from an active binary system, II Pegasi, where SWIFT triggered on this as if it were a gamma ray burst, and then after getting the narrow field instruments, realized that it was consistent with a known cataloged X-ray source. We can see From the spectroscopy of looking at the ratio of helium to hydrogen like iron lines, you can get a temperature constraint along with the Bremsstrahlung continuum, and there's evidence for this changing during the course of the flare. So that's consistent with our understanding of cooling happening in the decay phase of a stellar flare. On M Dwarfs, there was another trigger by Swift. This was actually seen by another GRB satellite as well, the Kronos. The light curve is shown on the left, and the spectrum right after the trigger is shown on the right. So you can see that tail into the hard X-rays, where the peak temperature is about 140 million degrees. The increase in flux was about a factor of 7,000 compared to the non-flaring characteristic X-ray flux of this star. And this is it's a gamma ray burst at 5 parsecs, basically. Another example of the very young stars. This was another Swift triggered burst on a system that has an age of about 30 million years. Again, very energetic events, very high estimated X-ray to bolometric luminosity at peak. The X-ray spectrum can either be fit by a very hot thermal plasma or non-thermal emission. What you're seeing on the right here is the light curve of the event, showing the XRT light curves, and there's actually 2 events here. There's the big first flare, and then the very creatively named F2 is the second flare event, and then some of the UBOT filters that we're also catching data. One of the interesting things that I'll touch on a little bit later when I talk about radio observations, but when we look at the X-ray spectrum across such a wide energy range, we can investigate whether we really are seeing purely thermal plasma or whether there is any non-thermal contribution. On the sun, where flares do not get quite as hot, they get maybe 20 to 30 million degrees at peak, you can clearly see a prominent non-thermal Bremsstrahlung component above 10 keV. And it has been, I hate to use the phrase holy grail, but that has been one of the goals of studying large stellar flares, is to see if we can find evidence for these non-thermal particles. There's a number of reasons why this has been difficult. I guess the other thing I want to say here is that for this particular event on DGCVN, we were able to constrain a thermal temperature of 300 million degrees. The plot on the very right shows the expected trends of the radiative timescale for energy loss due to radiation, timescale for energy loss due to conduction, and indicated the upper limit to this flare timescale and the measured peak temperature of that big first flare, which probably coincidentally, but very suggestively lies at the intersection of those 2 curves, and suggests that there might be a maximum temperature that can be sustained in a stellar flare. When we put this together with solar flares, it's long been known that solar flares and stellar flares appear to have the same power loss slope in the relationship between the peak emission measure and the peak temperature. This is actually a kind of an old plot. It combines a very heterogeneous data set from different kinds of solar flares, from nano flares all the way up to the largest solar events, and then a sample of stellar flares, again chosen very heterogeneically. So it's been interesting that they do appear to show the same slope, but when you get to these very energetic events, there is evidence for flattening of this emission measure temperature trend. This is a bit of a PowerPoint science slide. I overlaid here some stellar flares that were seen by the MAXI instrument on the space station, some of the swift triggered flares that have been studied individually on the right. So you can see that as you get above 100 million degrees, that power law index does not seem to continue. There's been some suggestion that the emission measure temperature diagram is of something fundamental to the magnetic reconnection process. Shibata and Yokoyama, in a paper 20 years ago, they very used this in the title of their paper, which was very provocative, that perhaps there was an HR diagram of magnetic reconnection that you could diagnose by making this simple plot and then looking at the balance between conductive cooling and reconnection heating. You get different trends as a function of magnetic field strength and as a function of emitting length. And they suggested that maybe there was a main sequence for flares, which the sun would sort of be along, and then you could transition over to a giant branch for super hot flares. So it's interesting, as I said, kind of provocative, but potentially being borne out by recent observations. So let me move on to talk about one of the other things that I mentioned earlier, that along with flares, we recognize that on the sun, the most energetic solar flares often have ejections of mass, coronal mass ejections accompanying them. And this has been a growth industry in the last like 5-10 years. Again, I don't have time to go to do this separate topic justice, but there's been a lot of interest in the stellar community and the exoplanet community in trying to find evidence for stellar CMEs and study them in a systematic way, since there's a clear impact on habitability and space weather. This paper by Mason that I'm showing some diagnostics, little graphs from, pointed out a couple of different ways in which dimming signatures could be used to diagnose coronal mass ejections. And what you're seeing on the left is an example of a schematic for absorption dimming, where you've got your flaring loops, and then you've got your kind of blob of material that's getting ejected. And as that material covers the flaring region, you see a temporary increase in absorbing column that would then decrease as that material expands and gets more and more rarefied. The other kind of dimming, called mass loss dimming, is on the right, where you see here you've got your flaring loops, and a coronal mass ejection is an ejection of coronal mass. That mass gets lost. So if you're looking at the right temperatures, you can see a decrease in emission due to the fact that that mass has been lost. And in a paper that I was involved in, we looked at analogs between solar phenomena of coronal mass ejections and potential stellar phenomena for coronal mass ejections. These dimming signatures were identified as sort of the most promising lines of research. That was the emphasis for one of the emphases for the escape concept that was had an initial down select for the last SMEX call, but then was not ultimately selected. What you can see here are light curves of individual ionization stages of iron. So going from iron 24 in the upper left to iron 9 in the bottom right, and that you're seeing the temperature of sensitivity decreasing from things that are clearly responding to the flare to iron 9 at a temperature of a few million degrees is really more characteristic of the quiescent corona. And you can see that the nature of the response is changing as you're seeing the response to plasma heating versus the response to the ejection of mass. Absorption dimming, I think, is a promising signature of stellar CMEs. So just reminding you on the left what that mechanism would look like in a schematic sense. This was claimed to have been seen in a large flare from algal, originally analyzed more than 20 years ago. The data itself was not reanalyzed, but the results were reinterpreted recently. Sophia Moscou interpreted these observed NH variations as originating from a constant velocity self-similar expansion of a CME front. So it's basically, if you've got some amount of mass and matter that is expanding constant velocity self-similar expansion, you'll see the column density drop as t to the -2, which is consistent with what was observed in this event. One project I have been involved in, or not involved in, I've been leading when I have the time to do it, is looking systematically at all of these Swift-triggered stellar flares. I showed you some specific ones that have been published so far. There's about a dozen that have been observed over the lifetime of the Swift mission, and basically relaxing the assumptions of what usually we assume that column density is coming from the interstellar medium, which I don't care about, I'll be honest. But if you relax that assumption and allow NH to vary along with all of the other plasma parameters, we're finding that there are systematic changes in this trend as a function of time. That seems to be fairly common during these energetic events. And this is work in progress to assemble the data and then to kind of figure out what does it mean. Is it telling us that we're seeing absorption dimming as a fairly common occurrence along with along when these very energetic flare events happen? Is it indicative of something else? That's still TBD, but it's certainly very interesting. Let me just briefly mention some of the other diagnostics that have been used in the X-ray for coronal mass ejections. This is Chandra observations. There's now a second paper that has come out on a different target looking at blue shifted material in the cooler plasma that's probed in the X-rays. And this is a very busy sum of plots. What I want to draw your attention to is each panel is a different ionization stage. So you've got magnesium 12 with the Meg on Chandra, with the Heg on Chandra, and then oxygen 8. There's a light curve, and then there's a spectrum at each of these times with a Gaussian or multiple Gaussians that have been fit. And then on the very bottom plot, there's the inferred velocities as a function of time. And the thing that these authors pointed out was that the very coolest plasma, that oxygen 8 plasma, appeared to show an evident blue shift late in the stages of the flare. And they suggested that's evidence for plasma motions in a coronal mass ejection. Another paper that just came out recently looked at the M Dwarf EV lac, and basically they're looking at oxygen. No, that's oxygen 8. Okay, that's a typo in my slide. I apologize. Format is very similar to the format that I showed you before, but they found blue shifted oxygen 8 during the decay of a large flare, but not in higher temperature material, as suggestive of an outflow. Here it's traveling at less than the escape velocity, so there's some potential complexities to that interpretation. But it's another way in which coronal signatures can be used to diagnose these dynamic events. And I told you this was an area where there's been a growth of interest in the last few years. There's a paper in 2021 by Astrid Veronig looking at signatures of mass, looking for signatures of mass loss and dimming in light curves of active stars. And the idea here is that they're not making these ionization series light curves. Instead, they're looking at the total emission from the star, and there are clearly flaring events, and then there are things that are not flares, and their interpretation of these dips below a baseline level are that those are dimming events. Okay, so let me talk about some of the other wavelengths, since I can't help myself. But there's some interesting recent results. So back at the beginning of the talk, I mentioned how there were these Kepler detections of super flaring in slowly rotating G stars and K stars in the field, but not picked up by virtue of any other magnetic activity signatures, but still able to produce these very energetic flare events. A project that I have been leading with which Claire Bressour used to be an intern at the Space Telescope Science Institute, is now a graduate student at St. Andrews University, and is not almost submitted, it was submitted. We looked at overlapping Galax, NUV, and Kepler white light measurements during these flares. We had previously identified a population of short duration near UV flares, and we used the sort of serendipitous, simultaneously obtained data to probe multi-wavelength properties. And you can see some examples here. These are NUV flares seen at short cadence on the left. So the Kepler data is 1 minute cadence. The Galax data is 10-second binning in blue and 1 minute binning in dotted black line. There is no apparent evidence of changes in the white light accompanying these NUV flares. When we look at long cadence Kepler data, which is less favorable, it's a 30-minute cadence compared to 10-second cadence for Galax. Again, we see no evidence for any changes in the white light, and that is over a fairly large span of energies. So Galax energies, flare energies of 10 to the 36 ergs down to a few times 10 to the 32 ergs, and we can put limits on how large the largest flare would be in the Kepler band that you wouldn't see, and that's indicated there with in the graph. So the interesting thing is we can put all this together. We have over 1,500 targets that overlap between Galax and Kepler, and these super flaring G and K stars that have simultaneous white light and NUV measurements do not show the trends that we expect from either studies of solar flares or studies of and observations of highly active M dwarfs. What you're seeing here is a plot of the measured Galax band NUV energy on the x-axis, and then the y-axis is that ratio, as I said, of the maximum white light energy that could be occurring but not detected at the time of the Galax flare to the Galax band energy, flare energy. The points are all of the 1,500, the yellow, mostly yellow and green points are each individual flare measurement and upper limit, color coded by effective temperature. And there's 4 points from the literature of M dwarf, pointed M dwarf multi-wavelength observations, where you can see we've reconstructed the appropriate ratio. There's some black body curves on this plot, which are often used to interpret the white light and the NUV, and along with some more realistic radiative hydrodynamic simulations, which is the gray band. So M dwarfs read APJ, G and K dwarfs don't. All right, and so switching gears a little bit to another part of the electromagnetic spectrum, but one that's relevant for STROBE-X. In the last couple of years, there's been some unexpected results from the millimeter regime, probing flaring in nearby magnetically active stars. So the first couple plots I'm going to show you are from ALMA, but it's not just ALMA. Finding serendipitous and now targeted detections of millimeter flaring in nearby stars. The example on the right is the first one from Promisin, which of course is very nearby. The characteristics that were unusual, the wavelength was unusual to start with. But the time scale is unusual. These were very short duration, seconds to tens of seconds. In the millimeter band, there was a generally falling spectrum, which indicates optically thin emission, potentially linear polarization, which is very interesting because it points to the ability to be able to diagnose accelerated particles in stellar atmospheres. I mentioned for the hard X-ray flare observations, that's how solar physicists calculate their electron beam parameters from solar flares. They basically look at the change with time of the non-thermal Bremsstrahlung that shows up at hard X-ray wavelengths. We can't do that in stellar flares, or we have not yet been able to do that. And this is an interesting way to get at that information. It's not just M dwarfs. There's a paper that has been submitted showing evidence of these bursts on solar-like stars. This is an example of Epsilon Eridani. These objects were targeted because folks wanted to study disks around the stars. And I recall a conversation with one of my colleagues who studies disks shortly after Alma started taking observations. He said, we're looking at these disks and there's stars there. So it was a nice confirmation of something that I had hoped would show up. So I said it's not just ALMA. There have been some recent results in the last couple of years from these stage 3 cosmology experiments, the Atacama Cosmology Telescope and the South Pole Telescope. As they're getting closer to the galactic plane, they're finding things in our galaxy that are millimeter transients. And what was surprising to them, not so surprising to me when I heard about this, is that they are also confirming the usual suspects for stars with enhanced magnetic activity. So these are plots from, I think it's the Guns paper, showing the millimeter, the SPT data, along with TESS and assassin optical constraints, indicating that those actually are occurring during some relatively large flares. And these are magnetically active stars in the solar neighborhood. So exactly what you would expect to be producing enhanced flares. When we've probed some of these millimeter flares at multiple wavelengths, we're finding interesting results. The nature of the millimeter bursts by themselves suggests an extreme nature of events. These things can increase in flux by a factor of 1,000 at peak compared to non-flaring value, which is pretty low. This one multi-wavelength campaign on Proxima showed that there was an FUV burst of similarly short duration. That's the first time for this phenomenon, although there is NUV evidence, as I was alluding to previously. This is a same target, so it's Proxima, but different multi-wavelength data. And you can see there does appear to be an X-ray response to these. The couple of ALMA flares appear to be accompanied by very weak, but enhancements at X-ray wavelengths. So that's indicating that there's plasma heating happening in at least these case, in at least this case. And what is interesting is that while the millimeter and the FUV suggests kind of some extreme nature characteristics of these events, what we're seeing in the corona and what we're seeing in the white light flaring suggests that these are kind of pretty ordinary run-of-the-mill events. There's nothing apparently outstanding or spectacular from them from those perspectives. So with the continuation of those stage 3 experiments and the cosmic microwave background stage 4 facility, I think we can expect to hear more about millimeter transients in the future, and being able to connect those to transients or variability that's happening in other regions of the electromagnetic spectrum will be important for learning about stars, and not just compact objects and black holes and quasars and things. So I've laid out a couple of the areas where I've emphasized that we need to understand whether these scaling relations that have been established for the sun hold into these very energetic stellar events. There's an additional complexity as to whether stellar events can erupt. There's been some recent modeling looking at the coronal response to a flux eruption. And if the star has a heavy overlying field, it can actually suppress an ejection. And so it begs that question of, just because a flare happened, did a coronal mass ejection happen? And that has implications for the space weather and astrobiology effects of the stellar activity. So questions beget more questions. I think I took this from a white paper that was submitted to Astro 2020, and just relaying stellar astrophysics focused questions and how those questions translate in the context of habitability. So understanding things like accretion and magnetic activity in young stars, what factors control the emission of stars is important for being able to understand the long-term impact of that high energy radiation on a planetary atmosphere, and basically how things change with time. How do flares change with time? How do stellar winds change with time? We'd like to go from this is interesting to let's have a systematic examination of how important these things are. And maybe it's something that, well, we'll see. there's a lot of open questions there. So let me come to how STROBE-X can contribute to this area. So it's basically through measurements of extreme coronal activity through super flares on M Dwarfs, active binaries, nearby magnetically active G and K stars. As I showed you, those are contributing transient millimeter emission. We think that plasma heating should be accompanying those, and so being able to constrain that presence or absence will tell us about how far we can extend the solar flare model into different regimes of stellar objects, which is essentially the second bullet point. How does the solar paradigm hold under different conditions of temperature, density, field strength, length scales? The wide field monitor can detect these extreme stellar flares, and then by triggering slews onto them, study the evolution of flare properties. So that would be basically enhancing the kinds of examples that I showed from the Swift triggered stellar flares, but potentially on a much larger sample. And estimates from the white paper that Paul Ray put together of more than 100 flare triggers per year. I think I'm probably the person who came up with that number, and I don't remember how I came up with it. So it'd probably be interesting to look at the assumptions that went into that and see if that needs to be revised. And then another point in which STROBE-X can contribute is through this triggering and follow-up, constraining evidence for coronal mass ejections, particularly looking at the absorption dimming signatures. So I think this is my last slide with a conclusion. There's an exciting parameter space of stellar coronal activity that's inaccessible to smaller field of view pointed high energy satellites that something like STROBE-X can access uniquely. The bandpass and the energy resolution are key. You need both low energy and high energy, right? So the high energies tell you about the high temperatures, potentially non-thermal emission. The low energies tell you about the response of the more characteristic X-ray emission and evidence for any flare-induced absorption changes. And there's new developments at other wavelengths that I think bodes well for interesting results ahead. To learn more about stars, I like stars, as well as their connection to near-stellar environments. So thanks for your attention, and I'll stop here and take some questions.